Hey everyone, welcome. I am absolutely thrilled to have you here for today's explainer. We're going to be diving deep into the mathematical heart of machine learning today. Specifically, we're exploring some incredibly detailed notes from Arnemon's AI journal on Stanford's legendary CS229 course. Our goal? We're going to completely demystify linear regression. We'll start from the ground up with tangible, real-world data, build out the algorithms that learn from it, and then, my favorite part, we're going to uncover the beautiful statistical truth that explains exactly why these algorithms work as perfectly as they do. Let's get into it.
Think about this for a second. Can an algorithm actually predict a house's exact value before a for sale sign even hits the front yard? I mean, it sounds kind of like magic, or maybe just a really good real estate agent, right? But it's actually the entire foundation of supervised machine learning. The heavy math we're about to get into isn't just a bunch of numbers on a chalkboard. It's literally the engine driving predictive models all over the globe, answering real-world questions where the stakes and the price tags are incredibly high.
Okay, let's dive into this. Here is our roadmap for today. We'll kick things off with the supervised learning problem, define linear regression and cost, explore gradient descent algorithms, check out the normal equation shortcut, and finally arrive at the probabilistic why. All right. Section 1, the supervised learning problem, grounding the data. Let's move from those abstract concepts to a tangible problem we can actually get our hands on and solve. Picture this. You're out in Portland, Oregon, gathering some real estate data. You're jotting down the living area in square feet, the number of bedrooms, and the final sales price of 47 different houses. So, for example, a 2,104 square foot home with 3 bedrooms ends up going for $400,000. Now, because our goal here is to predict a continuous target variable, the price, based on input features like square footage and bedrooms, this is formally known as a regression problem. If we were predicting discrete categories, like whether it's a house or an apartment, well, that would be a classification problem. But today, we are talking strictly continuous money.
Now, to actually talk to a computer, we need a shared language. So keep this mental notation cheat sheet handy as we go. We use a lowercase m for the total number of training examples, so our 47 houses. N is the number of features, like bedrooms and area. The input variables are x, and our target price is y. And hey, a really crucial point here. When you see x or y with an I in parentheses as a superscript, do not multiply it by itself. That superscript I is simply an index pointing to a specific row in our dataset. It is not an exponent. Finally, theta represents the parameters or weights that we are actually trying to learn.
Moving right along to Section 2, linear regression and cost. Let's look at how we mathematically define this whole setup.
So we need a function to approximate the price, and we call this our hypothesis function, h of x. Here, we are deciding to model the price as a simple linear function of our features. We literally just multiply each feature, like square footage, by a specific weight, theta. But wait, notice that theta underscore 0 sitting at the front? To make all the underlying matrix math super smooth, we introduce a really clever trick, a fake feature called x underscore 0 that is just always set to the value of 1. That gives us our intercept term, which allows our line to shift up and down the y-axis, rather than being forced perfectly through the origin.
Okay, so what happens if we just guess some random theta parameters right out of the gate? Well, our predicted prices are going to be absolutely terrible. To fix that, we have to define a cost function, j of theta. This function calculates the difference between our hypothesis prediction and the actual true price from our dataset, squares that difference, and then sums it all up across all our examples. This right here is the famous least squares cost function. Our ultimate mission? Find the exact values of theta that minimize this cost function. Minimize the error and you maximize the accuracy of your predictions. It's that simple.
Which brings us to Section 3, gradient descent algorithms, how the computer learns. Time to see how the computer does the heavy lifting to minimize that cost step by step.
To actually get to the bottom of that cost function, we use gradient descent. We start with an initial random guess for theta, and we take iterative steps down the steepest slope of the error curve. To do this, we use the LMS, or least mean squares, update rule, also known as the Woodrow-Hoff learning rule. Let me translate this math into action for you real quick. The magnitude of our parameter update is directly proportional to our error. If our prediction is way off, the algorithm takes a massive corrective step. But if our prediction is already really close to the actual price, the error is tiny, and the parameters barely change at all. It makes total intuitive sense, right?
Now, there are 2 main flavors of this algorithm. Batch gradient descent is, well, it's meticulous. It calculates the error across the entire training dataset, every single house in Portland, before it takes a single step. For massive datasets, that is a highly costly operation. Enter stochastic gradient descent. This method looks at just one single training example, updates the parameters immediately, and moves right on to the next. Stochastic gradient descent is often highly preferred in practice because it starts making optimization progress right away. Sure, it might wildly oscillate a bit near the bottom, but it gets you close to the minimum dramatically faster. All right, section 4, the normal equation shortcut. Let's look at a totally different, much more elegant way to solve this.
What if we didn't want to blindly step down a slope at all? Armed with some matrix calculus, we can explicitly take the derivatives of our cost function and just set them to 0. This leads us directly to the normal equation, theta equals x transpose x inverse times x transpose y. This is a breathtakingly elegant closed-form solution. It acts as a total shortcut that completely skips the iterative stepping, the learning rates, and all that looping of gradient descent. It just gives us the exact parameter minimum right away in one clean mathematical sweep.
Finally, section 5, the probabilistic why, uncovering the statistical truth. We have the algorithmic how down, but now we arrive at the absolute climax of our explainer.
We've been using the least squares cost function this whole time. But honestly, why use squared error at all? Who decided that squaring the difference between our prediction and the actual price was the absolute best way to train a model? Why not use the absolute value, or raise it to the power of 4? I want to show you that least squares isn't just some random, convenient guess by early computer scientists. It is deeply, beautifully, statistically justified.
Let's think back to those Portland houses. Our linear model looks at square footage and bedrooms. But what about all the stuff we completely ignored? The unmodeled, real-world perturbations. Things like the mood of the seller on a given day because they hadn't had their morning coffee yet. Or a slightly better school district boundary. Maybe the weather when the buyer visited. Because there are so many of these uncorrelated random noise factors adding up in the real world, the central limit theorem from statistics tells us that we can safely assume these overall error terms follow a Gaussian or normal bell curve distribution. And here is where the absolute magic happens, the crucial twist. If we assume our errors are Gaussian and independently and identically distributed, we can ask a new question. What are the parameters that make our specific data set the most highly probable to have occurred? We define this as the likelihood of the parameters. To make the math a bit easier to chew on, we take the log of this likelihood. When we use maximum likelihood estimation, MLE, to find the theta that maximizes this probability, the math beautifully simplifies. Because of how the Gaussian equation works, maximizing the probability literally leaves us with a negative squared error term. And maximizing a negative term is mathematically identical to minimizing a positive term. Boom! By simply trying to maximize probability, we mathematically arrive at the exact least squares cost function. It is just a stunning convergence of statistics and machine learning.
You know, this actually perfectly illustrates a tiny but super important distinction in terminology that trips a lot of people up. The actual equations for likelihood and probability are exactly the same. But if you view the equation as holding the training data fixed while you vary the parameters theta, we call that the likelihood of the parameters. If you hold the parameters fixed and look at varying the data, well, we call that the probability of the data. In machine learning, our data is fixed. It's the houses we already observed, so we are maximizing the likelihood of our parameters.
So we've gone from basic square footage to matrix calculus all the way to proving that minimizing squares is identical to maximizing probabilistic truth. So I want to leave you with this final thought. If the seemingly random pricing of houses in Portland follows such a rigorous, beautiful mathematical truth just waiting to be modeled, what else in your world, in your daily life, or your business is just waiting to be predicted? Thank you so much for hanging out with me for this explainer. Keep questioning the data, keep learning, and I'll catch you next time.